Okay, on to the back of the worksheet. Now, in the last column of that chart, they added 0.5 moles of NaOH as strong base. That would have completely neutralized our acid. It would have shifted the equilibrium all the way to the right. So in theory, this would go all the way to the right. We'd end up with 0.5 molarity of our acetate ion. All the H pluses would have been robbed by the OH minuses, and the acid would be 0. Well, I can't put that into the Henderson-Hasselbalch equation. I can't put 0.5 over 0 into that, because we all know that dividing by 0 is infinity, and you can't take the log of infinity. Okay, great. So, what happens now? Well, you only have the acetate ion left. But we know that it's a weak base, because acetic acid is a weak acid, so the conjugate base will always be a weak base, because it's in equilibrium, so both are happening. I know the Ka for acetic acid, or at least they told me the pKa. I can definitely use that to figure out the Ka. The acetate ion is the conjugate base of that acid, so his Kb is going to be related to his Ka according to an equation that we've used that's on our reference tables. Ka for an acid times Kb for its conjugate, these guys must be conjugates of each other, equals Kw, which is 1.000, probably infinite sig figs, times 10 to the negative 14. Okay, now, I didn't know the Ka, I knew the pKa. Let's see, the pKa was 4.76. pKa is negative log of the Ka. So of course, the Ka equals 10 to the negative 4.76. I can put that right there, and when I put it into my calculator, I'm going to be very careful with scientific notation. Maybe I hit enter a lot. Anyway, I end up with a Kb, and if you haven't found this yet, pause it and try it out, and try and figure out what Kb is. Okay. I got Kb to be 5.75 times 10 to the negative 10. That makes sense because negative 4.76, this is negative 10, but that's a larger number. So this is sort of like negative 9, and this is sort of like negative 5, adds up to negative 14. So it does make sense. Okay. What was the point of this Kb? We have the acetate ion in solution. That's all we have. The weak acid has been totally neutralized. So we're going to take this acetate ion, we're going to make it do its own equilibrium, like every base does, and we're going to use this Kb to figure out what's going on. Here's the acetate ion acting like a base. Put it with water. It's going to take a proton off the water, become acetic acid again, leaving the OH minus concentration. This starts as 0.500 molarity. 0, 0. We just found Kb. Kb equals. And of course, Kb equals that guy and that guy over that guy at equilibrium. So let's make it do its thing. Plus x minus x. So products over reactants raised to their coefficients of 1. Why did I screw out the water? He's a liquid. These three guys are aqueous. The water's a liquid, so he's not involved. So I got x squared over 0.5 minus x. I really have 3 sig figs. I'm going to do a bunch of math, keep more sig figs than I need, round to 3 sig figs at the end. What's my goal? Well, ultimately, I want the pH. If I find X, notice what X is. X is the molarity of the hydroxide ion. If I know that, I can take the negative log of it. I can find the pOH. If I know the pOH, I can find the pH because they should add up to 14.